Yesterday we were talking of regular singular points and irregular singular points. Okay, and we had seen that if we are able to express our equation in this manner, qx upon x square y equal to 0, right? Where both p and q, the easiest way to check whether a particular point, okay. Yesterday, did we do it with x or did we do it with x minus a? Okay, let's
X minus
I'm
A.
writing. Yeah, it was something like this, right? X
Yes, ma'am.
minus a, right? This was the equation that we were talking of, right? And we discussed the fact that x equal to a becomes a regular singular point, if both px and qx are analytic functions at x equal to a, right? Now, when we are talking in terms of x minus a, as in the earlier cases, see, we can have two types of series, something like this or something like this, right? So whenever we are talking of series in powers of x minus a, that means we are interested in the point x equal to a, right? But when we are talking of series in powers of x only, that means we are interested in the point x equal to 0. Okay. Now, simple mathematics tells us that even if we have something at x equal to a, we can always shift the origin. We just have to make a transformation, x minus a. Okay. And our new variable, the original variable x, gets changed to a new variable t. And what happens is that for t, the origin can be taken as 0 because for x, the origin was a, right? So everything can be transformed to studies around 0, even if we have studies around x equal to a, right? So that is why, and the second foremost reason being that it's easier to talk of convergence of series of this kind rather than series of this kind. Okay, so that is why we are more interested in the point 0 being ordinary, being singular, okay, or being regular singular or being irregular singular. Okay, so that is why, though we define in terms of x minus a, but ultimately the same definition can be carried over for x equal to 0. Okay, so that means if I have to define the fact whether x equal to 0 is a regular singular point or not, I am interested in an expression of this kind now. Is this okay? Now, the point is, how do we talk about px and qx? Like yesterday, we said both px and qx have to be analytic at x equal to a, right? Analytic at x equal to a means they should be functions that that can be expressed as convergent series, okay, or they are series that converge to some function, then they are analytic at x equal to a. So that means when we are talking at 0, the same definition goes for px and qx, right? Now what happens is that at times it becomes difficult to check whether they have a convergent series or not. Okay, but in some cases it becomes easier, but in some cases, see, in case they are both polynomials, it's okay. But in case they are not polynomials, then it becomes difficult to test whether they are convergent power series or not. Okay, so to do that, what we can do is that we just have a simple rule that if both px and qx, when what we can do is we can find this limit extending to 0 px and limit extending to 0 qx. See, now note that we are interested in the point x equal to 0 only. Okay, so that's why we are evaluating this. Had it been the other case, we would have evaluated limit extending to a px and limit extending to a qx, right? In case both these limits are either finite or 0, okay, then we assume that both px and qx are analytic at x equal to 0. In case any one of them turns out to be infinity, okay, either this or this, in any one of them turns out to be infinity, then we can say that x equal to 0 is an irregular singular point. Are you getting my point? So if even if this is infinity or the other is, any one of them is infinity, then x equal to 0 becomes an irregular singular point. Okay, so to we but we are not interested in irregular singular points. We would be interested only in regular singular points. Okay, so that means what do we want? We want these limits to be finite or zero. Even if they're zero, it's okay, because then that means they are polynomials or they are convergent to something, right? But then they do not have to be infinity. Like for example, say like just look at the Bessel's equation that we had. So that means, say, okay, I'll start with the Bessel's equation and then I'll tell you how to go about it. The Bessel's differential equation was something like this: x square y double dash plus xy dash plus x square minus n square y equal to 0. This is a Bessel's differential equation of order n, right? Now, in the back end, keep this differential equation in your mind: x y dash plus qx upon x square y equal to 0. Okay, that means the moment we have to test whether it is a single ordinary point or a regular singular point, we just reduce our differential equation in this form. Okay, that means I can write this as y double dash plus 1 upon x y dash, right, plus x square minus n square upon x square y equal to 0. Okay. Now compare this differential equation with the standard form and identify your p's and q's. Okay. Now in this case, what is your px? If you compare this term with px upon x, it's already written in this form, something upon x. So definitely the numerator is your px. So in this case, your px is 1. What is it? A constant polynomial. Okay, and therefore analytic at everywhere. So it is not a problem. That means my px in this case is an analytic function at x equal to 0 as well, right? Now compare with this qx. Now this has to be of what form? Qx upon x square, right? So if you compare this, then how much is your qx? It's simply x square minus n square, which is again a quadratic polynomial. Okay, so that means my qx is also analytic at x equal to 0. So that means what? Both p and q are analytic at x equal to 0, and therefore I can conclude that x equal to 0 is a regular singular point. Are you getting my point? So what you have to test is either p and q both, they are polynomials, number one. In case they are not polynomials, then we evaluate. Polynomials means direct simple polynomials, not rational functions. So in case they are not polynomials, then we evaluate the limits. And then we have to test whether x equal to 0 is a regular singular point or an irregular singular point. So this, see, Bessel's came up with this kind of a result. And that's why he said it is a singular point, but it's a typical kind of a regular singular point. See, as I mentioned, regular singular points are those singular points from where singularities can be removed. So if the singularities can be removed, then they become as good as ordinary points. And therefore, the logic of finding a power series solutions for such differential equations becomes valid. The only problem is that maybe we do not have the same kind of power series solutions as we have for ordinary points. So we may have to change the procedure of finding the power series solutions for regular singular points. But it does not mean that power series solutions do not exist for such points. Is this point clear? Hmm? Is it okay or not? Any one of you can take the initiative and answer. Is this clear or not? Because this is
Yes,
an important concept before we move on. Hmm? Okay or not? Okay.
yes,
Now,
ma'am.
in contrast to that, okay, fine. In contrast to that, just consider this differential equation. Okay. Now, again, as I said, just write it in the form that we want, right? So, what would it be? Y double dash plus 1 upon x upon 2x cube y dash plus 3x upon 2x cube y equal to 0, right? Now, what do I want? I want the expression this to be something upon x, right? So, what I do is I rewrite this equation as 1 plus x upon 2x square upon x. लिख सकते हैं ना इसे,
Yes, ma'am.
right? Plus 3 by 2 upon x square y equal to 0. Is this okay? Because that's what I said. This should be your first step now, because we need p, we need q. And how do we find p and q? Mind you, they are small p's and small q's, not capital P and capital Q. Okay, so there is a difference between the two. So we want this. See, this was capital P. And what is capital P? I mean, what is small p? X capital P. So that is why we write it as small p upon x, small q upon x square. Okay. Now, from here, I get that my px is 1 plus x upon 2x square and my qx is 3 by 2. Okay. Now, as far as my q is concerned, it's just similar to the previous problem, right? It is what? It is a constant polynomial. And therefore, q is analytic at x equal to 0, right? Now look at p. Though it is a polynomial, but it is a rational polynomial. So we cannot conclude anything here, right? So what do? That means for this, we need to compute limit x tending to 0 px. Okay. And what will be limit x tending to 0 px? It will be limit x tending to 0, 1 plus x upon 2x squared. Now, how much is the limit here? Hmm?
Infinity.
Infinity,
Infinity.
right? So that means what? That means my P is not analytic at x equal to 0.
Analytical.
Yeah. So that means in this case, though Q has turned out to be analytic, but P fails to be analytic. So therefore, we'll conclude that x equal to 0 is an irregular singular point. Okay, so that's what I said. There you'll have only two options with you. Either both p and q will turn out to be simple polynomials. In case that happens, x equal to 0 is a regular singular point. In case they fail to be normal simple polynomials, then we have to compute the limits. It could be that we have to compute the limits for both p and q. No problem, we can always compute the limits. Computing limits is never an issue. Okay.
Yes, ma'am.
So, and sometimes, what happens is that they look as if they're going to be complicated terms, but ultimately they turn out to be very simple polynomials and computing limits. See, even while computing limits, maybe you have to use L'Hopital's rule also at times, because ultimately you are computing limits. Right? Say, for example, you may have something like sine x upon x, you know. So, I mean, functions, they are, of course, sine x by x is a standard function. We know the limit, right? But when we are evaluating limit x tending to 0 px or limit x tending to 0 qx, we might end up with functions that are actually indeterminate forms. But we know how to compute the limits for indeterminate forms as well. So, that's what I said. Computing limits will never be a problem. In fact, what we do is we call, uh, like like if you see your book, you will see that they define it as, they call this term as p naught, which is what? Small p evaluated at 0. And what is that? Limit extending to 0, small px. Okay, so p evaluated at 0 makes sense when your p itself is a polynomial. So just put x equal to 0 and you get the value. We call that as p naught, right? But in case we have to evaluate the limit, then whatever is the limit value, that becomes my p naught. And mind you, this p naught cannot be infinite. That's why we will not consider the cases when we have irregular singular points. Similarly, your q naught will be q evaluated at 0, which is nothing but limit x tending to 0, small qx. Okay, see, again, I mean all these are interrelated. You see, when I'm saying my p naught is limit x tending to 0, small px, isn't it same as limit x tending to 0, x capital px? Right? Similarly, my q naught, which is limit x
Yes,
tending
ma'am.
to 0, small qx, is it same as limit x tending to 0, x square capital qx? So that's why I said, I mean, there is a relation between them, which we not forget. So either way is right. I mean, but then follow one way because you will not forget it then. So I would prefer to just identify your small p, identify your small q. So for that, what you have to do is just write your differential equation in that standard form, identify your small p, identify your small q, evaluate them at 0, and get your p naughts and q naughts. Is this clear? Hmm?
Yes, yes, ma'am.
Hmm? So, I mean, why this is important, because see, I'll tell you. Once Bessels came up with the fact that yes, we have regular singular points, and we can find power series solutions for such regular singular points also. Then the question mark was, what kind of power series? See, the point is that we cannot have the same kind of series here. Why? Because this kind of series becomes valid only when x equal to 0 is an ordinary point. Okay. Now, even if x equal to 0 is a regular singular point, it still is a singular point. And because it is a singular point, that means it is not an ordinary point. Because it is not an ordinary point, that means I cannot have a series like this. See, because this is what the theorem has been proved for. So though we did not do the proof, but this is what the theory says, the theorem says. Okay, so that means even if I have x equal to 0 as a regular singular point, this kind of a series will not work. Though I know it will have a power series solution, but now the question mark is, what kind of power series? Okay, so for that, Frobenius came up and he said, let us consider this a series of this form, where n still varies from 0 to infinity. Okay, says, okay, we do not start with the 0 power of x. See, what is the difference between this series and this series? Here, the series is something like c0 plus c1x plus c2x square and so on and so forth. That means what? That means you are starting with x equal to 0 in this series, and the series is in increasing powers of x, right? But what would be this series like? It will be like 0, c0 x to the power r plus c1 x to the power r plus 1 plus c2 x to the power r plus 2 and so on and so forth. That means what? It is a series, but it is in increasing powers of x to the power r, not x. See, there is a difference here. Now, obviously, your question should be, क्या फर्क पड़ रहा है? No, फर्क पड़ रहा है. See, when you are starting in increasing powers of x, that means your first term, that means gradually the series is building from a constant function to a linear to a quadratic and so on and so forth. But here the series is already starting from a function which is some power of x. So it is not starting from scratch. It is starting when you plot series, when you plot sequences or when you plot series, what do you get? You get dots, right? And those dots ultimately define the function to which it converges. Fine. Now it is like you are not starting from one, some point on the x-axis and moving on. You're already starting from somewhere here and then you are building it on. Okay. So that's why, this kind of an infinite series is called as a Frobenius series because it was given by him. Okay. Now the question should be, how do we find this R? You know, I mean, of course, for different differential equations, my R will vary. And depending upon this R, I will have a different kind of series. You know, my R can be my R can be an integer, my R can be a rational number also. My R can be, or in other words, my R is a real number, right? So the question is, what kind of R is going to be useful to us? Number one. Number two, how do we find the R? I mean, this R for a given differential equation, how do I know that what R should work for that differential equation? Okay, of course, as far as C0, C1, these coefficients are concerned, we know how to find them, right? Because this is what we have learned. I mean, we just equate the coefficients to zero, we get a recurrence relation, and we are able to get a power series. So finding coefficients is still known to us. The problem is how to find this R. That is the second question. Third question that we are going to answer is, depending upon the values of R that we get, how are we going to write the solutions? Okay, so this is what now we are going to learn further on. Okay, so for this, what we do is we'll start with a general differential equation and then see, how this works out to be. I mean, how to find this R, right? I mean, this is how the theory has been developed for the theorem, uh, which we call as the theorem itself is called as the Frobenius series solution. Okay. See, our differential equation is something like this: y dash plus qx upon x square y equal to 0. Okay. Or in case you want to write it in a simplified form, it is something like this: plus pxy dash plus qxy equal to 0. यही था ना? ठीक है. Now, we are assuming two things here. Number one, that x equal to 0 is a regular singular point. Okay. Now, because x equal to 0 is a regular singular point, that means both P and Q are analytic at 0, at x equal to 0. Okay. Now, if they are analytic at x equal to 0, that means they can be expressed as convergent power series of x. Okay, because they are analytic at x equal to 0. So I say, I mean, of course, I'm not writing that reason which I have just spoken. I'll assume that let my px be something like this: p naught plus p1x plus p2x squared and so on and so forth. And let my qx be q naught plus q1x plus q2x squared and so on and so forth. Why? Because both P and Q are analytic at x equal to 0. Is this point clear? I mean, I'm just writing the assumptions here. The first was this. And because of this assumption, I have this. So this is basically not an assumption. This is a consequence of this assumption that x equal to 0 is a regular singular point. Okay. Now I say let y equal to summation Cn x to the power n plus r, n from 0 to infinity, be a solution of, I mean, do we number that? I did not number it. Let's number this equation as 1. Okay. So I say, let this be a solution of 1. And now this is assumed. This is my assumption that let C naught be non-zero. Why do we want C naught to be non-zero? It will be proved later on, number one. Number two, that means always we ensure that my Frobenius power series starts with x to the c naught x to the power r. See, in case of earlier power series, we did come across certain situations where c naught was 0. So that means what? That means our series was starting from c1x and other terms. Maybe all even terms c naught and subsequent even terms were 0. So that means my series had only the odd terms. And that's why the series started with C1x, right? But here we are assuming that my C naught is non-zero. So because my C naught is non-zero, that means the first term in my series is always going to be this. C naught x to the power r. Right? इसके बाद कैसे behave करते हैं वो कैसे होता है, that we are leaving for the time being. Is that okay? So these are the two assumptions that I have made, that x equal to 0 is a regular singular point and y equal to z x, this kind of a series is a solution and where c naught is non-zero. Okay. Now follow the same method that you have done earlier. Okay. In the sense that find y dash, find y double dash, and then substitute in your solutions. Okay. So in this case, your y dash will be summation n plus r cn x to the power n plus r minus 1. Okay. N varies from 0 to infinity. Now, in this case, we don't have to bother about that because my C naught is non-zero. Similarly, my y double dash will be summation n plus r minus 1 cn x to the power n plus r minus 2 n from 0 to infinity. Okay. Now, in the earlier case, when we used to find the derivative, because of the presence of C naught, when you find y dash, the derivative of C naught is 0. Therefore, your y dash always started with C1. So that is why we had the summation n from 1 to infinity. But in this case, the derivative, see, your first term is C naught. So if you, that means, see, if you want, you can write it down. Your series is, you will see this, your series is something like C0 x to the power r, C1 x to the power r plus 1, plus C2 x to the power r plus 2, and so on and so forth. So when you find y dash, it will be r c naught x to the power r minus 1, right? So that means your summation is still starting from n equal to 0. Similarly, your y dash will be r minus 1 x to the power c r minus 2 c naught. So, okay, so subsequent terms. So that is why in all these summations, our n will always start from 0 to infinity. So that is why whether you write them or not write them, it is understood that your summation starts from n equal to 0 to infinity. Is this point clear to all?
Yes, ma'am.
Right? Now we move on as we did earlier and we substitute in the differential equation. Okay. Now what was your differential equation? Your differential equation was x square y double dash plus pxy dash plus qxy equal to 0. And mind you, what was your px? It was something like, you will have p0 plus p1x and so on and so forth into y dash plus q0 plus q1x and so on and so forth into y equal to 0. This is what we have defined our p's and q's to be. Is that
Ma'am,
right?
will it be
Ma'am.
px y dash or px or into x y dash?
No, why? Why will we have px into x y dash? This is not capital P. Oh, okay, okay. Oh, right. I'm sorry. Did I? Right. Yeah. I am so sorry. It should be xpx plus qxy. ठीक है ना?
Yes,
So,
ma'am.
huh. So even here, I'll have xpx and here I'll have x. Is that okay now?
Yes, ma'am.
Right. Now when you substitute, you are going to get something like x square into, what was y double dash? Summation, what is that? N plus r, n plus r minus 1, cn x to the power n plus r minus 2. यही था ना? Of course, where n varies from 0 to infinity. Fine. Plus, the next term was x into p naught plus p1x plus p2x square and so on and so forth into summation n plus r cn x to the power n plus r minus 1, where n varies from 0 to infinity, plus q naught plus q1x plus q2x square and so on and so forth into summation cn x to the power n plus r, n from 0 to infinity equal to 0. Is this right? इसमें तो कोई गलती नहीं है.
No, ma'am.
No, ma'am.
Right. Now I can combine this x square with this term, combine this x with this term, and then see. That means I have summation n plus r minus 1, cn x to the power n plus r, n 0 to infinity. ठीक है?
Yes, ma'am.
Plus, now see, this has become a little cumbersome. Okay, p naught plus p1x plus p2x square and so on and so forth into summation n plus r cn x to the power n plus r, n from 0 to infinity. Okay, this x will get combined with this, and the last term will be something like q0 plus q1x plus so on so forth into summation cn x to the power n plus r equal to 0. Is this right? I mean,
Yes,
just
ma'am.
do it yourself, as I can commit a mistake as I did earlier also. Okay. So please cross check. Do it simultaneously with me. Huh? Right. Now, I say, what will be the coefficient of x to the power r? Can you find it? Coefficient of x to the power r. When do you get that? When n is 0? Obviously. है ना?
Yes, ma'am.
So from the first term, what will you get?
R into R minus 1 C naught.
R into r minus 1 c naught. What about the second term? Now this is interesting.
Ma'am, 1 plus R into R C1.
1 कहाँ से आ गया? I'm saying x to the power r.
Okay,
From the
ma'am.
second term, what
Second
will be the
summation.
coefficient of x to the power r?
R
It's a
C naught.
product of two series. ये term कहाँ गई? px ये कहाँ गया?
Ma'am, then the coefficient will be series.
I'm saying x to the power r.
Yes, ma'am. So we are putting n is equal to 0. Then
हाँ.
it is also containing a series with it. That is
But
P naught plus P1x.
what will happen when p1x gets multiplied with this term? What will be the power of x?
Power of x will increase.
So We don't want that. We just want x to the power r. Hmm?
R P naught
Ma'am,
C
we will
naught.
consider only P naught.
Yes. So what do you get?
Ma'am, R P naught C naught.
R P naught C naught. ठीक है? What about the last term then? Again, x to the power r only.
Q naught C naught.
Q naught C naught.
It will be plus q naught c naught into x to the power r into x to the power r. यही होगा ना? What happened? Now again, see, the point is why I started with x to the power r, because that is the first term which this series is going to start with. What will happen? See, it's what we do earlier also. We used to collect the coefficients and then see how things are behaving actually. The point is that from these three expressions that we have written, the smallest power of x will be r. What will be the next term? X to the power r plus 1. So we'll have more terms there. Then x to the power r plus 2 and so on and so forth, right? Now, in the earlier cases, we used to collect the coefficients and get a recurrence relation for ourselves, right? But in this case, we are more interested in finding the value of r first, and then depending upon the value of r, we are interested in finding the recurrence relation. Okay, so I'm now just building up the theory how to find the values of r here. Now, because we had some positive terms equated to 0, that means the coefficient of x to the power r will also always also be 0. That means what? That means you will have an equation of this form, plus q naught c naught equal to 0, which I can write as c naught into r minus 1 plus r p naught plus q naught equal to 0, right? But what was our assumption? Now you have product of two terms equal to 0. तो आप क्या कह सकते हो? Either C naught is 0 or this is 0. But what was our assumption? C naught is not equal to 0. So this was the reason. Okay, that because we wanted our very first term in the series to be x to the power r. Okay, not more than that, right? So since C naught is not equal to 0, that means the only alternative, the only option we have is that this term should be 0, right? Now, just a few minutes back, I told you what is P naught. P naught was limit extending to 0 px, and what was Q naught? Limit extending to 0 qx. So we can always find these values, and they are finite, mind you. That is why x equal to 0 was a regular singular point. तो इसका मतलब क्या हुआ? In this equation, except for r, all other terms are constant. So basically, what is it? It is a quadratic equation in r. Okay, this equation is called as an indicial equation. Okay, how many roots will it have? Because it's a quadratic equation. That
Two
means
roots.
you are going to get two values for r, r1 and r2. So these values of r that you, and see, they are going to be differential equation specific. Why? Because p naught and q naught are differential equation specific. So depending upon my p and q, I am getting these coefficients, and depending upon these values, I am getting my roots. So my roots can be real and distinct. My roots can be real and repeated. My roots can be imaginary. So that means the values of R1 and R2, see if R1 and R2 are both real and distinct, that means I have two power series solutions here. So one will be of the form Cn x to the power n plus R1, the other will be Cn x to the power n plus R2. So supposing my R1 is plus 1, R2 is minus 1. Okay, so that means one series will start with n plus 1, the other series will start with n minus 1, and so on and so forth. My R1 and R2 can be repeated also, depending upon this equation. Okay, so that means what we have to do is, now I won't do much here because I just want you to be, uh, I mean, not do much, but do problems based on this. From your exercise 8.3, your problems 1 to 8, and in fact 9 to 16. They are both similar. The first 16 problems are similar. So basically what you have to do is, I'll just quickly wind up what we do. We given the differential equation, we express it in this form. Okay, this is the first step we are going to do. We identify our P, we identify our Q, verify whether x equal to 0 is a regular singular point or an irregular singular point. Okay, find P naught, find Q naught, find the initial equation, and find the roots of that initial equation. Bas, itna step. Okay, how to write the solution, how to find the solution, we'll do it later on. These are your problem numbers 1 to 8. From 9 to 16, instead of 0, you have x minus a. Okay, so don't have to do anything here. Just change your variable. Define t as x minus a. This is what the exercise also says. Okay, you have to just define your t as x minus a. So now your new differential equation, which is in terms of t, so what x equal to a was doing for your original differential equation, t equal to 0 will do for your new differential equation. Okay, so identify. Now using this fact, now work for t equal to 0. If t equal to 0 is a regular singular point, then x equal to a will also be a regular singular point. Okay, so I mean, do for t and conclude for x. Is this clear?
Yes, ma'am.
Right. So
Yes, ma'am.
first 16 problems of your exercise 8.3, you have to do in this manner. Okay. So I'm winding up the class now, and